You are in the meeting now.
Recording in progress.
So I will change this one. Okay, so when you have ultimate limit states, we have two checks. One is a bending, other one is shear. Okay, so for bending, m star should be less than or equal to pi m u, e star less than or equal to pi v u. Okay, so these are the two conditions. So if you look at, this is a quick summary of what we learned. Okay, so when you look at the rectangular section, we'll go to the T section in a minute, but rectangular section, so the standard notations are B, capital D, small d. So for the bending, use this condition to find the pi is 0.8, so pi is equal to 0.85, so 0.85 if Ku less than 0.36. Okay, if Ku less than or equal to 0.36, pi is equal to 0.85. So the mu, we use approximate rectangular stress block. Okay, I think that is clause 813. So in that one they talk about approximate rectangle for the stress block. So it is something like this is the, okay, it should be comes next to that one, but the dn, the standard notations, this is gamma dn alpha 2 f dash c. So this is the approximate rectangle. So this is the neutral axis. Yeah, this is the neutral axis. So we should be able to write the FC here, and actually if you go FST, yeah, so FC is equal to uniform stress, so stress time area of concrete. So this one, this is gamma dn, and say gamma dn somewhere here. So that's if it is a same width, if it is the same width, so that is b times gamma dn. Yeah. So when we use equilibrium equations, this equal to that. Yeah. So FST is equal to stress times AST. Okay, AST is the area of tensile reinforcement. This is yielding strength. Okay, so the tensile reinforcement will always reach the yielding point if this one is satisfied. Okay, if this one is satisfied, definitely this will reach the yielding point, so we can use FSY. So we use two equations. What are the two equations? Equilibrium equation, yeah, and the moment equations. Yeah, we use the two equations. FC is equal to FST, that is the equilibrium equation. This one equal to that, and the moment mu is equal to force if equal and opposite parallel forces. So that distance z, so z times force, it can be FST or FSC, both are same. Okay, so using this one, we should able to solve this one. Okay, so we should able to, so if you know the mu, so you should able to if you know AST, that means steel area is given, so you need to find out mu. So the steps are find dn from equation 1, then check for KU dn upon d equal or less than or equal to 0.36, then find mu from equation 2. Okay, so m star should be less than or equal to pi mu, so from that find maximum m star. So that is the capacity. Yeah, this is the maximum moment we can apply if you know the AST value. If you know the AST value. If you don't know the AST value, if you know m star, if you know the m star, go backward. So m star is known, so m star from that mu should be greater than m star upon pi. Pi is equal to 0.85. Okay, so you know what is the mu, what is mu, the minimum value. Okay, find minimum what is the minimum mu. Okay, what is the minimum mu. So if you know the mu, so you know the mu, so you have two equations. You have two equations with two unknowns, AST and dn. These are the two unknowns. Okay, so you have two equations. These are the two equations, and you know the FC and FST, everything. The two unknowns are the AST and dn. Okay, and solve for AST and dn. So you'll get the AST and dn. So dn need to be checked. So K is equal to dn upon d. Okay. If it is satisfied, we can proceed. EST need to be checked. What are the checks we need for the EST? Minimum AST, having is 8.6. Give me a second. All the close numbers are given in the study guide, but 816 I think. Give me 1 second. So 816. So that is close number 816. So then we also need to check the spacing. actually it's from the crack control. So that is close number 86. 861. So the maximum spacing in this close, they said maximum spacing is equal to 300 millimeter. Okay, and also it cannot go from the wall. You cannot put it more than 100 meter apart, so that need to be checked. So that's all for these moment things, for the bending things. You may have two type of questions. Okay, two type of questions. So tutorial 2, second tutorial, question 1 have both of this one. Okay, so tutorial 2 part A is this one, part B is this one. Okay, part A and part B are given there. Okay, so this is for singly reinforced section, so we consider the reinforcement only here. So if you look at the tutorial question that we discussed last week, but someone need some quick revision. So when you have all these values, here's the first question. Generally this one is easier. Okay, so this one is much easier compared to this, because here you have AST, so there is no difficult calculations or anything. Just go to this one, so you know the FC value, you know the FST value, so everything is known except Dn here, except Dn. Gamma alpha 2, everything is given in this clause. There is an equation. Okay, so you will substitute alpha and gamma. If dash C is given, B is given, we don't know the Dn, but FSY is 500 MPa. This is given 4 in 20 bars, so you should have the AST value. So in the first part, the question 1, AST is given 4, say 4 in 20. So this is the 20 millimeter bar, 4 in 20 bars. Okay, 4 in 20 bars. So this one 314 square millimeter. Okay, so you will get 4 of that, 52. So you know the AST and you know the FSY, that is in type. In type means 500 MPa, alpha 2 and gamma, they gave the equation. This is 0.85 minus 0015 F dash C. This is 0.97 minus 0.0025 F dash C. They said both should be larger than 6.7. So you know the F dash C, 32 MPa. So you substitute 32 here, and you should be able to get alpha 2 as 0.802, this one as 0.89. So both are larger than 0.67, so I should be fine. So I know here FST is known, EST is given. So in FSC, alpha 2 I can calculate, F dash C is given, B is given as a 250, gamma I calculated, only Dn is unknown. So this one is equal to this, that is the equation first. So you should be able to calculate the Dn. Just substitute everything, equate this one to this. This one and this one are equal. Just equate that one. Everything is known other than the Dn. So you should be able to calculate the Dn, that is 110 millimeter. The answer is given, but please work out. Okay, if you read the solutions are given to check your progress, not each and every steps. Okay, so Dn is known and check for the Dn. Okay, so the Ku value we calculated, that is 0.31, so it is less than 0.36. So I should be able to proceed because it's 0.36 is satisfied. So all my assumptions are correct. So then Mu equation, you know that. So the Z value, this distance from here to there, from here to the steel, that is D, small d. So you know the FST, FSY, AST. Okay. So here Z is equal to D, from here to there is a D. This is gamma Dn. It's a midpoint, so half of gamma Dn. Okay, so you know this value. This is 250. Gamma already calculated. Dn we already calculated as 110. So we should be able to find out Z. Yeah, we should be able to calculate Z. So if you know the Z, this one everything is known, you should be able to substitute. Make sure the units, you have to use everything in megapascal, millimeter, Newton. So this is one set of units. Okay, when you substitute, everything should be megapascal, millimeter, and newtons. Okay, so it can be millimeter squared or millimeter cube, but it's everything millimeter. If otherwise, it should be pascal, meter, Newton. So that is one set. Don't mix up. Okay. If you use meter for the area, length of this, so it should be pascal there. Okay. Unit is important. So when you substitute everything, so it become Newton millimeter. So Newton millimeter, you'll have a very large number. Okay, so 10 to the power minus 6 kilonewton. So 1 Newton millimeter is equal to okay. So that means you need to divide this answer into divide will okay. So you should just substitute and you have answers. Is that okay? Or yeah, hopefully you should be able to do that, isn't it? I don't need to work out step by step. Anyway, I already work out, but only I don't substitute. Hopefully you should be able to substitute, isn't it? Anyone have issues with that? Yeah. So the second part is M star is given. If you need any explanation, please stop me. Otherwise, because I can't see you, okay? Because it only shows who are the people attending. That's all I can check. So I don't see any of your faces. So if you don't understand, please stop me and ask. (150 kilonewton meter). Okay, so 150 kilonewton meter. Question is, how much steel I need? How much steel I need? So that is comes to this one. Sorry, the second part. Okay, second part belongs to this one. So because M star is given. So M star is given. So here M star is given. So we need to follow that part. So I need to find out mu first. So mu should be greater than or equal to M star upon pi. So this is 150 divided by 0.85, 176.5 kilonewton meter. Okay, so my mu should be larger than 176.5. 176.5. So the question is how much steel I need. Okay, in the first part we use 1252 square millimeter steel. Okay, we might get the mu value from that. Okay, so if you work out, I take the mu value there for the first part, it's 189. So when you use, it is 189 kilonewton meter. So when you use 1252 square millimeter steel, you get this one. Now we need this much of mu at least. So the steel is the question. So if you look at this first part, you know, we need little bit less than this one, yeah, slightly less, because more steel means more moment, yeah. So I need this one. So we have two equations, Fc is equal to Fst. That means you'll have alpha 2 F dash C gamma dn times B is equal to Est Fsy. That is the first equation. Second one is mu so mu should be larger than that one, so I take the lowest value. Okay, so mu is equal to Est Fsy d minus gamma dn by 2. So in this one, what are unknowns? We know this value, we know that value. Okay, so we know all this one. So the unknowns are Est dn, here also Est dn. Okay, so two unknowns, all others are known. Okay, when you substitute mu, so mu we use 176.5 10 to the power 6 Newton millimeter. Substitute as a Newton and millimeter. Okay, so 10 to the power 6 Newton millimeter. So we have two equations you should be able to solve. I think so how to use the Excel to solve it, otherwise you can use your program calculator to get the solutions for these two equations. Two unknowns, the second order equation. Okay, there will be second order. So you will get from here, you will check Est, so you'll get that one 1157.6 millimeter square, and the dn is equal to 101.36. If you substitute and solve these equations, I think I explained how to use Excel to solve it, and in the study guide I give the solution for these two equations to find out Est. If you know the Est, you should be able to substitute and get the other values. It's not a problem. Okay, if you know one, other one can be obtained. So in the study guide, if you look at the study guide, I gave the equation for Est. So I gave something like that, alpha 2 F dash C Fsy minus s square root, and we have some terms here. Okay, so that is given in the study guide. The P is the steel ratio, Est divided by Bd. Okay, so if you look at the study guide, the solution is given. So you can use, you don't need to memorize the solution. There are two equations, it's algebra, you should be able to solve them. okay, using Excel or your program calculator. So we have these two, but we need to do the checks. So first one for the DN, $350, so you will get 0.29, so that is so satisfied. Yeah, so that second one is the minimum, AST minimum. So if you go to the close number 816, they gave an equation. Okay, alpha 2 is equal to 0.2 for rectangular section. So they gave the minimum steel ratio in 816. So if you substitute values, it become 155.2 millimeter square. So that means you need to, what is that means? Minimum reinforcement means you should provide at least 155.2 square millimeter. Whatever the moment, even if you get a very small moment, you still need to provide at least 155. But we are providing 1157, so it's much higher than the minimum reinforcement. So this is EST is larger, so we don't need to do any other changes. Okay, the spacing, we don't need to worry about it because the width of the beam is 250, so you cannot exceed the spacing more than 300. So all the checks are done, all the calculations, all the questions are answered. Okay, any questions here?
No, sir.
Yeah, if you have anything, just stop me and ask. So the next question is a doubly reinforced section. So generally when you have, normally we work out how to calculate the capacity for singly reinforced section. Singly reinforced section means we provide the reinforcement on tension side only. There is no reinforcement for compression side. Okay, so that's why we call singly reinforced section. So when you have singly reinforced section, we provide on the tension side, but we also need the shear reinforcement. Okay, so for generally for the beams we might need to provide some shear reinforcement. To hold the shear reinforcement, we need to provide some 2 bars on the top. Okay, so that comes from the detailing as well. We'll talk about the detailing a little bit later. So we'll have some reinforcement bars to hold the shear reinforcement. Okay, otherwise it won't stay there. So that one also can be considered as a doubly reinforced section, but normally what we do is we do the singly reinforced calculation, and those the opposite compression side reinforcements normally provided from the detailing. Okay, from the detailing. So if you want to optimize further, because you know there are some reinforcement on the top, you should be able to use doubly reinforced theory to reduce the reinforcement on top and bottom, because you know definitely there will be some reinforcement on compression side. Okay, but at the moment we don't expect that one for your project. But doubly reinforced section sometimes we also require for the design. Okay, the doubly reinforced section means we provide the steel and tension and compression. So there are two chances we'll get the doubly reinforced section. As I explained, we will provide some extra reinforcement on the compression side, even though that is not required by design. For the design calculation, we don't consider as a doubly reinforced section, and single reinforcement is more than enough for the given moment, but we have some steel on the top. That is for two purposes. One is for to holding shear reinforcement, another one is from the detail. So if you have some extra reinforcement in the compression side, technically we may able to reduce little bit tensile reinforcement as well, because there will be some reinforcement at the top, so technically we should be able to reduce it. So we can consider this as a doubly reinforced section and calculate the capacity. So that is one way we should be able to do. But sometimes that is, so even though we don't design as a doubly reinforced section, it comes as a doubly reinforced because of the detailing requirements and the requirement to hold the shear reinforcements. Okay. But sometimes we need doubly reinforced section. Okay, doubly reinforced section. So if you have some big bending moments, then we might need doubly reinforced section. Okay? Because if you look at this one, we have here Ku is equal to, just look at these two values, a few values, okay? So 0.29 and that one, okay? So when you have dn or Ku value is 0.29, the MU is here, and when dn is here, so you can see when the Ku is equal to 0.31, we have 189 moment. When we use 0.29, the moment is 176. So that means as we increase the dn, the mu will increase. Here dn increase from here to there. Here dn is 101, here 110. So dn increase, so moment increase. Okay, so we technically increase the dn so that the mu can go up. So how to increase the dn? The depth of the neutral axis can be increased by putting additional steel. Okay, more and more steel will increase the dn because we put more and more steel at the bottom, so the neutral axis will move downward. Okay, so you increase the steel, the neutral axis, so the AST, you increase the steel, so the neutral axis will move downward. Okay, neutral axis will move downward, so dn will increase because dn measured from here. So you increase the AST, so the neutral axis will move downward, so that means dn will increase. What is that will do? Mu to increase. Yeah. So from the first question, so we have now we just calculate the AST as 1158. Just put 1157.6. Okay, so the dn is 101.36, 0.29, 176.5. Okay, in the first part we have 1252, 110.31, 189, I think 189. Okay, so you can see the EST increases, dn increases, so you put more and more steel here, the neutral axis will move downward. Yeah, neutral axis will move downward, so dn, the distance from the top fiber to the neutral axis, will increase. So that's happening here. So when dn increases, Ku will increase. As a result, finally we'll have more Mu. What is the problem? We can't go more than 0.36. Okay, we can't go more than, so you might increase, but the limit here is 0.36. You cannot go. If you go more than that, what will happen? Here pi will reduce. Okay, so if you go more than 0.36, pi value will reduce. So what happened, even though you increase the steel so that the Ku increases, Mu might increase, but pi Mu may not change much. Yes, whatever the increase you give in the Mu will be compensated by the pi reduction. Okay, so the increase in the design capacity is not very significant after 0.36. So in that case, if you need even more moment, we will use the doubly reinforced section. Okay, doubly reinforced. So doubly reinforced section have two things. One is comes due to the detailing and holding up the shear reinforcement. So in that case, technically we provide some steel and that will boost the capacity. Okay, because now we only consider singly reinforced section. So for example, for this one we provide 4 bars and we end up with 189, but we provide some additional steel to hold the shear reinforcement. We don't calculate anything, we just put 2 bars there to hold the shear reinforcement. So that means we have some force there. Definitely you have much higher bending moment than 189. So still our design is safe. Okay, but you may able to do some optimization. But other case where you don't have, you can't increase the AST further, but you still need to increase the moment. So if you can't increase the AST, due to the limit of KU, but you still need more capacity, we will go for doubly reinforced section. So if you have a doubly reinforced section, and how to calculate, that is a question 2. So the question 2, we have reinforcements here and we have reinforcement there. Okay, I don't know that. So the standard notation, this is called ASC, this is AST. Okay. Still the notations are same. So this is D. So we have new dimension, this is called DSC. The D distance, S for steel, C for compression. So the distance for this compressive steel from the top. So this is D effective length. Okay. So the neutral axis we don't know. So this is what we have studied in the singly reinforced section. So we have an additional term here at this line, FSC. Okay, so one additional term. So this is alpha to F dash C, all others remain same. So it's nothing changed other than the additional force in the compression zone. Okay, so still same equation for this and this. Okay, still same equation for this and this. So FSC is a new term, ASC times FS, not Y, because we don't know whether it's yielded or not. So it can be FSY, or if it is yielded, okay. Otherwise, so if the steel compression strain is similar, then you need to consider this equation, Hooke's law. So how to find out? This is the compression reinforcement strain. This is 0.003. This is dN. This is DSC. So using similar triangles, you should be able to calculate. Yeah, using similar triangles, this divide by that equal to this divide by this. So this divide by that, dN minus DSC equal to 0.003 divided by dN. So you should be able to, at the moment we don't know the dN. dN and ASTs are unknowns, or if you ask to find out AST, but in this case AST is given. Okay, AST is given, but we don't know the dn is always unknown in the most of the questions. Okay, so the dn is unknown, so we can't calculate the compression reinforcement strain. So what we need to do, we need to assume this is not yielding, because normally compression reinforcement will not reach the yielding point normal. Okay, so we need to assume so if you bring it up, okay, we assume this is less than yielding strain. So Fs, if it is less than, greater than this one, otherwise this one. So E is times this one. So this is 200 times 10 to the power 3 megapascal. So if you substitute this much of, if you substitute here, so you have the strain, so this is Fs. So Fs is equal to, so this is the strain, this is the strain in the compression reinforcement. From that I calculated the stress in the compression reinforcement. So this may not reach the yielding point, so that's what I assume. So the Fs should be less than 500. Okay, so this, remember, this is we assume. So we work out and find out the strain once we got the dn, and we need to ensure the assumption is correct. Okay, otherwise you need to go, if the assumption is wrong, so here you need to write the equilibrium equation. Fst is equal to Fsc plus Fc. So here you substitute everything, find out dn, because all other informations are known. So dn is calculated, so we need to do two checks for dn now. One is the usual check, Ku you do this one, that is a usual check. And we also need to check our assumption, because this is my assumption, because we don't know whether it's a yielding or not. So this is my assumption, so I need to check whether my assumption is correct, otherwise the Fs should be Fs1. Okay, so we need to calculate the strain, because dn is known. So if you substitute dn, you should be able to find out the strain in the compression reinforcement and check that one, whether that is less than the yielding strain, which is, what is the yielding strain? 0.0025. Okay. So if the assumption is correct, you can proceed. If the assumption is wrong, then you need to redo by putting Fs equal to, because assumption is wrong, so it should be here, So Fs equal to Fsy. So you need to substitute Fs equal to Fsy and resubstitute here and find out the new dn. Okay, so if your assumption is wrong, you need to redo the calculation by substituting Fs equal to Fsy. Okay, so you have the dn now. The question is, what is the moment? In this case, there are three forces. Earlier we have only two forces, two equal parallel forces acting in opposite direction last time, okay, for single wave. Now we have three forces, so it is easier to take the moment about one point. You can take moment about any point. This one is easier because this will be cancelled out. So this one times this distance plus this one times that distance, everything that distance. So I have provided the full solutions and we discussed this one last week, but is that clear now? Yeah? Is that okay?
This one and this one is a value.
Hmm?
This one and this one that is a value.
Hmm. So say if the dn, I think there is a solution. The solution.
Any case, this one is here.
Yeah, 0.0.
Yeah, and this one, yes, is same.
Yeah, 200.
Yeah, okay.
So because the yielding strain for the N type. Okay, so the question. So ES, the steel Young's modulus is 200 gigapascal. You should know that one. Okay. For concrete, you can get it from the table 312. For concrete, but for steel, you should know only one value. Okay. For steel, it will not change, but for concrete, it will change. So this should be known. N-type bars, Fsy is 500. That also will not change. Okay. Steel property, only one values you should be able to remember. So to find out the yielding strain, the stress is equal to Young's modulus times strain. This is a Hooke's law. Yeah, this is the Hooke's law. So Fsy, yielding stress, equal to yielding strain. Okay. So if you substitute, this is 500. This is 500 megapascal equal to 200 giga, so 210 to the power 3 megapascal times y. Okay, both are megapascal, so yielding strain is equal to 500 upon 200. So you get 0.0025. Okay, so this one you should know. Okay, because that's not changing.
Not change.
It will not change for the N-type bars. Okay, so you should remember. So it's that one here and that one here. Okay, so when you put the dn normally you should be able to calculate. I think in the solution I calculated dn value and recheck the strain. in this question, if you remember, this is the question, doubly reinforced. Okay. So here you can see dn is calculated as a 59. Yeah, dn is calculated as a 59.1 millimeter. So then I check the compression strain, that is equal to 0.003 dn minus dsc divided by dn. dsc is 40, and if you substitute dn as a 59, you will get the strain in compression reinforcement as 0.00097. So that is less than 0.0025. So my assumption is correct. Okay, my assumption is correct. Otherwise, I need to rework. From this point. If my assumption is wrong, I need to rework from here, because the compression force will be area of compression reinforcement times 500, because now the strain is larger than yielding. So if my assumption is wrong, because earlier I assumed the compression reinforcement will not reach the yielding point, so that's okay. But if the assumption is wrong, that means compression reinforcement reach the yielding point. So in that case, the force in the compression reinforcement, this component, become area of compression reinforcement times 500. Okay, so you should redo the calculation from this step. So this, only this component will change, so you will get new dn. Is that clear? Okay, so then I work out the mu calculation. Sorry. Here you can see the mu calculation and calculated in 104 as mu, then m star is 5 mu, so it's 88 kilonewton. Please work out by your own. Is it clear now what to do for the doubly reinforced section and what to do for the singly reinforced section? Any questions? Any questions? Someone? So let's move into the shear, then we will go to the tutorial 1. I'll quickly run through the tutorial 1 as well. So here, that is a shear. So anyone have any problem with the calculation for the flexural things? Everyone is okay? I'll take the silent as yes. So no one speaks, so I assume that everything is okay. Yeah. Okay. We'll go for this next one. So we had 10-meter long simply supported reinforced beam. They gave the cross-section detail and the reinforcements are given 2 in 24 bars, and the load is given, design load is 32, and ask you to design so you need to design I think that's a typo. The word there should be removed. Okay, so the word should be removed. So design required shear reinforcement for the beam. So don't put, I think there's a should be cut. Okay, there should be cut. Okay, so now it's a simply supported beam. The design load is given. Shear force diagram you should be able to draw. WL by 2, WL by 2. So the shear force, maximum shear force is WL by 2. W is given 32, L is given as 10 meter. So if you substitute 160 kilonewton. So if you ask to design shear reinforcement, there are certain steps you need to follow, that's all. There is no much complication again. So the first one, check for maximum design capacity. All the close numbers are given, okay, in the study guide. So BU max 0.55 sin theta V cos theta V. Okay, so this is the what is VU max? This is the absolute maximum. Okay, so VU, our design capacity VU cannot exceed this one. Okay, my design capacity VU value cannot exceed this one. So this is absolute maximum. If your shear force is larger than this capacity, we can't do anything with the shear reinforcement. So we need to change the section. Okay, but generally this will be very large value. So the details are like this. B is equal to 250. And we have reinforcements. The overall depth, capital D, is equal to 600. So we need this D value, and they also talk about the shear reinforcements. Okay, so I need to calculate the D first. D is equal to capital D overall depth minus cover minus diameter of shear reinforcement minus half diameter of tensile reinforcement. So 600. The cover is given as a 25. We have to get the cover, section 4. Okay, section 4 will give the cover minus diameter. Sorry, it's a question or you? Okay. Shear reinforcements. They said 10 millimeter bars for shear reinforcement. Main reinforcements are 24, so half of that. So you will get 553 millimeter. So that is D, effective depth. So now I need to find each and every value to get the VU max. So if you see 0.55 F dash C, what is F dash C? 25 megapascal. That is given. BV, the width of the web, so it's same V, so that is 250 millimeter. DV is a maximum of 0.72 capital D or 0.9 small d. So you need to calculate both. So this is 600 and this is 553. So you need to take the maximum of these two values. So you will get 497.7 millimeter, that is dV. And theta V we can calculate, but for the reinforced concrete we use a simplified method. The simplified method say 36 degree. Okay, the close number is given. All the close numbers are given 8243. Okay, 8243 say theta V is 36 degree. So if you substitute all the values, VU max is equal to 813.6 kilonewton. Pi VU max for shear force, pi is equal to, for shear force pi is equal to 0.75. For bending 0.85. For shear it is 0.75. For columns it is 0.65. Okay, 0.85, 75, 65. So you need to substitute 0.75 times 813.6. You will get 1/4. So 81.3 times 0.75. So it is 610 kilonewton. So you can see this is much higher than our shear force. Shear force is 160, so it's much higher than the V star. So we can proceed. Okay, so this beam technically can carry up to 610 kilonewton. Okay, so up to around 600 kilonewton I should be able to design the shear reinforcement. Okay, so that is the first step. I ensure my beam can carry the shear force. That is good. So next we need to check whether shear reinforcement is required or not. Just check for whether shear reinforcement is required. So we need to check whether the shear reinforcement is required. Okay, so let's say generally we'll see if we don't have the shear reinforcement what will happen. So generally the VU VU comes from VUC plus VUS. Okay, so this is the capacity. The maximum is this one, but this is the capacity. Okay, so this is the capacity. This capacity cannot exceed the UV max. So we already checked that one. That's okay. So VU, the shear capacity of the reinforced concrete beam, is equal to VUC plus VUS. What is VUC? It is contribution from concrete. This is contribution from steel reinforcement, the shear reinforcement. So first we will try without this one. Okay, so let's say there is no shear reinforcement. So what, and see whether the concrete itself can carry that. So we'll check whether the concrete itself can carry the shear force. So in this case, let area of reinforcement, area of steel reinforcement is equal to 0. Okay, or very small. We don't need to provide. So just checking that one. So in that case, it is less than minimum reinforcement. So in that case, VUC is given as KV BV dV square root of F dash C. Okay, so this is the equation for VUC. So if the shear reinforcement is very small, they said KV is equal to 200 divided by 1000 plus 0.13 dV. Okay, I am checking this one. So dV is known. dV is how much? 497.7. Okay, so if you substitute, you will get 0.121. They said it cannot exceed 0.15. This is the maximum for KV. KV cannot exceed 0.15. So I use that value because this is less than 0.15, so this is okay. So I substitute the KV here. BV is 250, DV is 497, F dash C is 25. So I'm going to substitute. So the VUC is equal to 0.121 times 250 times 497.7 times square root of 25. So if you do this one, so this become this much of Newton, so you will get 75.6 kilonewton. Okay, 75.6 kilonewton. So what is this? Without any shear reinforcement, the capacity of shear capacity of concrete without any shear reinforcement, this is the capacity of the concrete. Okay, so in that case, pi VUC 0.75 times that is 56.7 kilonewton. You can see this is smaller than V star. V star is 160, isn't it? We calculated earlier. V star is 160, but the concrete can carry only up to 56. Okay, so what does that mean? So that we need we need shear reinforcement. Okay, so if we need the shear reinforcement, let's see, VU is equal to VUC plus VUS. V star should be less than or equal to pi VU. Okay, so VU should be greater than V star upon pi. Okay, so if you say that one, so VU should be V star upon pi. So I have this one 160 kilonewton. Okay, so now I need to find out each and every term. So VUC is KV times VV dV character C. Remember, now we need the shear reinforcement. We cannot use this VUC because this VUC is when ASV is 0. Yeah? So now ASV, the area of shear reinforcement, need to be at least minimum or more than that. Yeah, because we need the shear reinforcement. This is what we need to calculate. So area of shear reinforcement need to be provided. So when you provide the shear reinforcement, at least you need to provide the minimum. So that means our reinforcement will be either minimum or larger. In that case, KV is equal to 0.15. So if you substitute VUC 0.15 everything, you will get 93.3 kilonewton. So this is the shear force the concrete can carry when you have some shear reinforcement, so a little bit higher. So if you substitute everything here, 93.3 plus VUS should be larger than 160 kilonewton 0.75. Everything is in kilonewton here. So if you calculate, VUS should be greater than 120 kilonewton. Okay, should be. So I need the contribution from the shear reinforcement more than 120 kilonewton. So what is VUS? We have an equation for VUS. ASV for S. All the close numbers are given in the study guide. Okay, so it is 8.2, section 8.2. If you look at the 8.2 section, you will have so I just equation for VUS. So this one is 500 MPa. This one 497.7 millimeter, we already calculated. This one is 36 degree. so cot theta. So if you work out, if you substitute everything, you will get ASV upon S greater than 0.35 millimeter squared upon millimeter. Okay, so that means the ASV upon S should be larger than 0.35. Okay, so I need to provide this much of shear reinforcement. I will explain how to give the detail, but this is the value we get from the equation. In the same time, so I need to check ESV minimum. ESV minimum, there is an equation, so that means the minimum area of shear reinforcement, given by this equation. So here that 25, 250, 500, and if you substitute, you'll get 0.2. So they said at least you need to provide 0.2, but we are getting more than that. So this is smaller than ASV upon S. So we need to provide this much. But if this one is larger, we need to provide that one. Okay, so this is the absolute minimum. You cannot reduce shear reinforcement below that one in case you need to provide the reinforcement. If you don't need the shear reinforcement, no problem. But if you need to provide shear reinforcement, you need to provide at least this much. So now we need to provide the shear reinforcement as per this one. So the shear reinforcement is sitting like this. So ASV is the area of shear reinforcement. So when you cut the beam, we have one bar here, another bar here. This is in 10 bars. Okay, in 10 bars. This is in 10 bars. So we need to provide something like the shear reinforcement. When you cut it, you have two legs. That means ASV is equal to 2 times the area of 10 millimeter bar. That is 78. You can find out pi r squared. So 156. This is the area of shear reinforcement in any cross section. Okay. So if you substitute there 156 upon S. So if you bring that one, it should be less than or equal to 445. So the spacing, so if you look at the beam, the main reinforcement will go like this. You might put some reinforcement on the tops. Then we need to provide the shear reinforcement. So this one is the spacing between the reinforcement. So the S should be less than 445, but we also need to check the limit. So S maximum spacing is 0.5 D for 300. So 0.5D, D is 600, so that is 300 as well. So maximum is 300 millimeter. We can go. Here they said the spacing should be less than 445. Spacing should be less than 445. But maximum is 300. So the answer is you need to provide N10 at 300. You cannot exceed 300. This is the maximum. But here the design said 445 is enough, but we can put in 445. Okay, so this is how we provide. So if you have very small spacing, let's say due to some calculation, if you end up with 44 or something, if the spacing become very small in this calculation, okay, sometimes you might, if you have very large shear force, you might end up with a very small spacing. So if you want to increase the spacing, you can do a couple of options. You can put multiple, legs. So this is 2 legs. So then you can provide another leg here. Okay, so we have 3 legs, so the area will increase. So you can increase the number of legs. Okay, so the spacing will increase, but this one quite large spacing, so we don't need to worry about legs. Okay, so that is shear. Any questions? So that is end of the tutorial 2 as well. Shall we go into the tutorial 1? Any question in the tutorial 2?
No, sir.
All good? Okay. So we have another 10 minutes, but I think we discussed the tutorial 1 already. But if you need anything, please stop me. So tutorial 1 is a little bit strength of material. Yeah. So we have, if I can't finish it, I will continue that one in the next Monday before we go into the slab. Okay. So the tutorial 1, you need to know a few things. First one is a serviceability limit state. So we assume, because in up to now the tutorial 2 is ultimate limit state. Okay, so we have 2 things. Ultimate limit state, the bending and shear comes under that. Now serviceability limit state, so the deflection, cracks comes under that. Okay, so 2 different limit states, so you need to be careful with the limit state and the assumptions. So in ultimate limit state, we assume, ultimate means almost near to the failure. Okay, so you can think the beam is going to break into 2 pieces or something, or can't carry any loads further. Okay, so that is extreme loadings. That's an absolute maximum. So it is ultimate limit state. So in that case, we assume the concrete cannot take any tensile force. Okay, actually concrete can take a little bit tension, but in ultimate we set the bottom part, okay, the tension zone, anything below the neutral axis cracked, so it cannot take any more loads. So we assume the strength of the concrete in tension as 0 in ultimate limit state. Okay, in ultimate limit state, we assume the strength of the concrete 0 because it's a crack. But even though that we have cracked section, the whole section still within the elastic. Okay, the cracking might occur while the compression and the steel are within the elastic zone, so it should be okay. So in serviceability limit state, we assume everything is within the elastic limit, but in ultimate we assume everything's almost near to the failure, so elastic zone no more valid in ultimate. But in serviceability, the loads are small compared to ultimate. The combinations, you know that factor of safety is 1 mostly. So the loads are very small compared to ultimate limit states. So the deflections will be less compared to ultimate limit states. So in this case, we should be able to assume, or we should be able to comfortably consider the whole section is within the elastic limit. Okay, even some of the concrete cracked should be fine, but still everything is elastic within the elastic range. So that is the main difference between the ultimate and serviceability. So don't confuse both. Okay, so sometimes you might think, oh, he used some equation to find out neutral axis in serviceability, but in ultimate he don't use that one. So all the equations we derive says something like this. So all these derivations and finding this is the neutral axis depth, okay, for one crack section. So this is the neutral axis depth for one crack section, and we have another equation for crack section. But remember, this one, these equations are derived, these equations are derived with the assumption of elastic behavior. So the section, the cross section is within the elastic range. So if you say that it is elastic range, we should be able to use all the theories we studied in our strength of material unit in undergraduate. So what is that? Area, second moment of area. So the meeting will finish in 5 minutes, so I don't going to explain this one, but I will explain the basic theories, then we'll continue next week before the slab, because from next week we'll have 4 hours tutorials. I put the lectures separately. Okay, so the question is, why he don't use this equation to calculate the neutral axis in bending calculation? Because bending calculations have different assumption. It's not within the elastic range. But now, the serviceability limit state, everything is within the elastic. So all the theories we studied in the strength of material is valid in serviceability limit state. Okay, the main theory, the important things in strength of material, when you have elastic section, okay, and the elastic, if the section is within the elastic range, the neutral axis will pass through the centroid. The neutral axis will pass through its centroid. Okay, do you know, how many of you remember the strength of material theory? Or should I quickly go through that one as well? Hopefully okay, isn't it? Yeah. So for the elastic material, anyway, we don't need lots of things there. For elastic materials or elastic sections, the important things, the neutral axis will pass through its centroid. Okay, neutral axis will pass through its centroid. For the plastic section, it is not the case. Okay, for the plastic section, it is not the case. So if it is a plastic section, generally the neutral axis will divide the area into two equal parts. Right. So in ultimate, mostly we are in elastic, plastic part. So we can't use that elastic theory. So the elastic theory said the neutral axis will pass through the centroid. So if you look at these equations, the YUC, Y bar equation, that is technically the centroidal calculation, centroid of the sections, okay, centroid of the sections are calculated. If you look at this one, what is the centroid of this cross section? So we have a rectangular section and we have some area over there. So if I ask you to find out centroid of that section, if I ask you to find out centroid of the section, that is marked as a Y bar UC, Y bar UC, that is a centroidal distance. Okay, it's not a rectangular section, rectangle plus something here. Okay. So if we can find out the centroidal distance of a cross section, that's what we are calculating here. Okay, so we will discuss this one next week and then go to the slab, because this again we need the slab as well. Okay, is that okay? So we will see you at 5 in 1 hour in drop-in session. Okay, see you then. Bye.